And welcome back to our part 2 of week 5, where we've been studying entropy, 9.3.1 on Apex. So this one delves into a little bit more when we start talking about a value for entropy, and what's going on when in a reaction. Does it change? What's going on? So first we start off with, we have salt, NaCl, sodium chloride. It's an ionic solid, made of sodium ions and chlorine ions. And when you dissolve this salt into water, do you think the entropy, so that, chaos, disorder, or randomness is going to increase or decrease when you dissolve it into water? Now, when you think about it, salt, you pour it into water, make salt water, you stir it up, everything's going kind of a little bit crazy and random. So it does increase the entropy because it is getting more, much less ordered after it dissolves. So you're increasing the entropy. This also is the same way when we're going from a liquid to a gas. So it changes the reaction involving gases as well. So the entropy is getting more. So, but we can look at this mathematically a little bit, in that if you look at the total number of moles before and after the reaction, you can get an idea. So if I look at this, where I'm taking hydrogen gas, oxygen gas, and I'm forming water, or water vapor, because it's the gas form. Now if you look on the left side of the arrow, the reactant on the left side, you have 2 plus 1, so you have 3 total moles on this side. Remember that 1's implied right there. On the right side, you just have 2 moles of gas. So meaning the 3 on the left side and the 2 on the right, there are fewer moles of gas after the reaction, meaning our entropy, our disorder, our chaos, our randomness has actually decreased because it's a smaller number. Because throughout the reaction, it's going to the smaller number, meaning your entropy has decreased. Now we can see this not only in chemistry and in chemical reactions, but you can see it in the Earth's continents, and you can see it around the Earth. That mountains, when you first start, they have more random assortment as it goes on, as it breaks down the rocks, and the dirt has more entropy, more randomness than the original mountain at the beginning, when it's more of that peak structure. And we kind of have this, that the slow change over time kind of encourages or reinforces this idea that over time things become more random and more entropy. So they look at this as saying that entropy of the universe is always increasing. It's always just kind of getting more and more random as it goes on. It's a slow or arrow of time, that the future will always have more entropy than the past. Okay. Now the whole idea, though, if the plate drops off a table, it breaks. Your entropy, it's, chaotic, it's random, it increases. However, the plate can never put it back together, like itself back together, and jump backward on the table, unless time went backward, unless you rewound the tape. So, but we can glue it back together. Does that mean you're making time go backward? Well, no, it's not going to be the same. It's not going to be everything kind of back to the way it was. And the whole universe is still increasing. The chemical bonds in your body that are breaking, increasing the entropy as you're putting stuff together. So it's kind of like saying the whole thing needs to be that. Now, we're getting into the whole idea we can measure it. As in anything in science mostly, or in chemistry, we have units and values for these things we're talking about. So entropy has the units of joules divided by, or per, moles times K. And so in the symbol is going to be the change of, or the triangle, S, change of S for entropy. You don't use E often because it's just been used for other things, so a lot of times it's kind of weird where in the world they get S from. Not too sure. They picked S for this. Okay, like enthalpy and what we did before, it can be measured. And so we have this symbol as well. Now the whole idea that as entropy is increasing, as you're becoming more and more random, you have a positive value. However, when you're getting more orderly, your stuff's coming together, the plate's being put together, it's negative. Okay, so this is kind of an important table to remember, probably because they're going to ask you a few questions back and forth. So as water is boiling, it's going to a gas. It's becoming more random. It's having more it's having more entropy. So if water, as it's boiling, has more entropy, it's going to be up here. So, what does that mean? Does it mean it's positive or negative? So if greater than 0, we have a positive. It is that one. Now, the other thing kind of reinforces what we were talking about before, is analyzing the gas reaction. Okay, what is the entropy change? So I go again. I count up how many moles on the left side. So you have 2 moles here, left side of the arrow, so 2 moles here. On the right side of the arrow, you have 2 plus 3. So there's 5 on this side, 2 on that side. That means the entropy is increasing because there's 5 on the right, meaning it's going up, meaning that it's going to be a positive one as well. Okay, when it's greater than 1, it's increasing. We have more randomness. So they have a few review questions at the end that, just going back to this whole idea of carbon, graphite, and diamonds, we know back to the beginning, graphite and diamonds are made of carbon. They're just solid carbon. So, and we learn the difference of them about enthalpy and energy. But why, with this idea they're trying to get at, is why you can't just turn graphite and pencil lead into a diamond. I mean, if we could figure it out, we'd make a lot of money. But which one has more entropy? So which one is more random? Is it this one or this? So the graphite or the diamond? Now the graphite's going to have more entropy because the arrangement of carbon atoms and layers are just allowing movement and randomness. Diamonds are not all random. They're kind of, that's why they're cleanly done. It's a crystal structure, so we have that. Now, diamond has a very low entropy, meaning it's pretty orderly. It's highly structured materials. But how are they able to form? If we say that the universe is trying to go to a more random, more chaotic, more kind of mess, why are they allowed to form? Well, the idea is you need a large amount of energy, and even high energy, high pressure, heat and pressure. This is coming from, Earth systems and the metamorphic rock. You need heat and pressure. Okay, so you need something more than just the arrangement. High pressure and temperature can add a lot of energy to put them into the ordered state. Okay. So what must happen as a diamond is formed from the graphite. So overall, we have the energy of must increase as well. Okay. So even though it's getting lower to form that diamond, for the diamond alone, the whole energy must increase. Okay. Last but not least, this is not the only thing. The only factors of enthalpy, which was from before, entropy, are not the only factors in determining what occurs in the world. Okay. This whole idea that we know the enthalpy of reaction is to turn graphite into diamond. It's just adding 2 kilojoules per mole. Well, that value of 2 kilojoules per mole is not a large amount of energy. So realistically, you could add in just a little bit amount. It's quite possible to change, this lead, just looking at enthalpy, into the diamond. Well, today, and what I just showed you there, we just talked about the entropy, and it's really only a negative 3.36, but it's not favorable because it's negative, meaning it's going to the more ordered state. However, it's not a big value, so why can't we ever see graphite turn into diamond? And you can talk about just kind of the ideas, not very long, but there's something else that's missing, and it's also why don't I just go outside, add a little energy, whatever, and I can change my pencil lead into diamond. Okay. Then the last thing it's kind of hinting probably as we move forward, we have thermodynamics, which we've been kind of doing, determines whether something happens, whether or not it will happen. Kinetics determines how fast. So we now need to know, there's another factor that determines whether or not it will be seen. So the rate of reaction, how fast this reaction is going to happen. And you've seen kind of this graph before in previous lessons or studies. You have the reactants, the products, so the energy kind of what it starts with, what it ends with. But there's a high activation energy for the reaction to actually occur. The higher this right here is, the slower the reaction. It's got to kind of go through this to make it to the other side. So carbon in your pencil may start here, but it requires a lot of this activation energy to get to the other side, which may, just looking right here to the end, doesn't look like a big difference, but you have to go through something to get there. So it's incredibly slow, way too slow to be ever to be observed. Okay, so that's the end of this one. Not a super hard or difficult thing, that the whole idea of entropy and the randomness, chaotic, kind of different things going on. So, good luck.